Check, check, check. Okay, good morning. Give me a second here. We're getting ready to get started. Okay, I was just waiting to see if we have some people show up here for the face-to-face. I'm going to go ahead and get started. Might be a relatively quick day. I didn't have a whole lot to say, so just kind of reminders up front here for anybody watching this after the fact. So I did go ahead and move up the assignment 6, so we're still working on that this week here. So remember, assignment 6 is on support vector machines. I plan to continue talking a little bit about kernel methods on support vector machines here. So the last half of the assignment that you're working on right now, not assignment 6, assignment 5, is due on Friday this week. So the last half of the assignment 5 on support vector machines actually has to do with kernels, kernel methods. So I thought I'd spend a little bit of time talking about that. We've got some materials from our textbook that discusses using kernels in the context of support vector machines. Also, Dr. Ng, so remind you about Dr. Ng's lectures, as I often do. He has in his videos about support vector machines. He has some good discussions also about not only about some of the details of how the support vector machine cost function actually works, but he does also talk a little bit about the kernel method and its relationship to kind of how it's related to support vector machines and kind of how it works and stuff. So yeah, I recommend if you haven't looked at that materials, do make sure that you take some time, go through it. Support vector machines are they're a good tool. They're a standard machine learning tool. They used to be kind of state of the art. I mean, probably nowadays, for many problems you'll be able to get better results using a neural network. So using some sort of even just a basic feed-forward neural network, if not a deep network. So, but support vector machines are a parameterized model. Same as logistic regression or in linear regression that we spent a lot of time with up to this point. So they work in the same way, mostly as a modification for the cost function. So I'm mentioning that because there are kind of two topics that aren't really from our textbook. So if you look at these, there should be some lecture notebooks on the k-nearest neighbors, which I might talk a little bit about today. So yeah, the 9.1 is for k-nearest neighbors. And then the second part for this week is some material on naive Bayes. Both of these came from really just some websites. Hopefully these I haven't had a chance to check. Hopefully these links, the primary sources, are still working for these. If you want to look at where some of this material came from. So, I mean, you might get some questions on KNN or Bayes on the test. We don't have that kind of in this assignment or the next assignment. But both of these are both of the machine learning methods that you're supposed to be looking at are a little bit different. They're kind of especially KNN, it's non-parametric, as I mentioned here in the announcement. So it works in a slightly different method, but I think it's good to these are also good ones to at least know the basics of, just so that you have some idea of kind of the different sorts of things you can use to build models of machine learning and kind of how they work. So KNN can actually make a good sort of first model for lots of projects. So it can be fast, and this non-parametric way so again, it's not really usually going to be state of the art unless you are working on a very simple problem where you'll get the best performance usually with something else. But it can often give you a good kind of baseline of what you can expect. And there's other uses for KNN, which maybe we'll talk about a bit today. I don't know if I'll talk too much about naive Bayes, but that's another one that's at least maybe good to read about and come across in a basic machine learning course. So. Okay, anyway, so let me just go ahead and check see if I have any questions. So as usual, if you have questions on the current assignment that we're working on, let me know. We still have today and Thursday. People need to ask a question about it. So maybe after I jump into kernel methods a little bit here, I'm going to come back at the end here and bring back up the assignment 6, although we already did bring that up last week and talked a little bit about the specific questions that are in the assignment 6. So, okay, so let me go ahead and start with kind of the stuff I was planning on discussing a bit today. So I began on this last Thursday, so if you're following along with our face-to-face classes, we did talk a little bit about get started on the nonlinear support vector machine classification. Okay, so in particular, so I'll repeat a little bit of what we finished up with last time. This is the treatment that comes from the textbook. So it talks about building a nonlinear support vector machine by basically applying a polynomial kernel. The stuff that we did to in our previous assignment is the same thing. We did it with linear regression instead of a support vector machine, but we did the same thing that's discussed here at the start of our textbook in order to get a nonlinear decision boundary for our parametric support vector machine model. Okay? So just real quickly, when you're using a polynomial kernel, you're doing the same thing that we did. It basically, adding in polynomial degrees for the different features that we have. Okay, so if you specify degree 3 for the polynomial kernel, like you do here, it's the same as using the that function that we used. What was the name of the function that added in the first degree, second degree, third degree, and the combinations of those for whatever features you have on the data set that we're looking at, right? So so just to get into a little bit of details of the actual lecture notebook that we're looking at that came from our textbook. This was using another one of those functions that makes a made-up synthetic data set, this make moons. the data set here is supposed to be for classification, and specifically it is supposed to be nonlinear. So a linear decision boundary is not going to work well, even with make moons with just two features. It's not going to have be linearly separable. So you won't be able to get very good results if you just use a linear, like logistic regression or linear support vector machine. So, so with two features, and if we're using a degree 3 polynomial here, really this is going to be doing the same thing that we did for our assignment. It's going to get the first, second, and third power for each of the two features, x1 and x2, plus also the combinations of x1 times x2 and x1 squared times x2, those kinds of things. All right. But once you have those, then you fit using the support vector machine cost function, right? Which didn't go into a lot of details of that, but the support vector machine cost function is basically these modifications here, where we use something to actually make it so that it adds in some idea of a margin, right? So it gives more of a penalty or more of a reward for separating things by the largest margin. That's kind of the effect, if you want to describe what these modifications to the cost function end up doing. Okay. So anyway, the downside of this, so this works. This gives you a nonlinear decision boundary, and you can think of that as an example of a kernel method. In this case, using a polynomial kernel is not going to give you good performance because it's basically exponential, right? So for this made-up data set, we've only got two features. So if we just use a degree 3 polynomial, we're only going to end up with an extra 10 or so features. And of course, you have to create all those features and then fit the model to those larger number of features. So, no big deal if you just have two features, but on a big data set where you have thousands or tens of thousands or millions of features, there'll be a very noticeable big performance hit for trying to do a kernel like that, like basically taking some number of polynomial combinations of your features. Right? So the number of features that you would end up having would grow exponentially. So if you're taking every combination of each feature times every other feature, you'll get a large number of them, the square. But it would be even more if you use the standard way that the polynomial features are generated here. So so that leads me to other, so we could be talking about, this is about where we left off last time, other ways of building different features so that when you fit a model to it, you'll get a nonlinear decision boundary. And there's others besides the radial basis functions, the Gaussian kernels that are described here, that can be used in the same way, but the standard one, the one that's used, both by default usually are these Gaussian radial basis functions, RBF kernels here. Okay. So the reason for that is these usually, most of the other kinds of variations of these are going to give you similar results, except for in special cases. So, if you do want to use a Gaussian kernel for support vector machines, probably just go ahead and try this first. This will give you an idea of how well a nonlinear kernel is going to work with a support vector machine. Another thing that I really is a little bit beyond the scope of this course, if you read Dr. Ng's treatment on kernels, or if you watch his videos, he'll go into it a little bit. But there's the so-called kernel trick, which it's because of the mathematics, you can actually apply a Gaussian kernel and not take a performance hit to do it. Okay, so and I'm not really going to go into the details of that, but that is kind of the explanation for why you'll often see kernels like these kernel functions introduced with support vector machines, because they can be used in conjunction with the support vector machine cost function to give a nonlinear decision boundary without any performance costs. Like I was kind of hinting at, the performance cost that would happen if you just take naively take the polynomial degree combinations of your features. So to step back, if you go through this part of our textbook, a lot of the stuff you're doing on the second part of the assignment is pretty much similar, or even the same as the stuff that's kind of shown and described here. Okay, so just to start off to understand, so the beginning of the Gaussian similarity functions, or the Gaussian radial basis functions, are that we're going to take the existing features and create new features as some function of similarity to these new features, these new landmarks that we pick in our feature space. Okay. So jumping ahead here a little bit, one thing that's usually done if you use a Gaussian radial basis function, it basically all of the features in the data set that's used for training are used as the landmarks. So we just start with those, and we calculate similarity to each one of the input for your training data set becomes a landmark, right? So our new features that we calculate from these are just similarities to the existing training data that we're going to be using. So just looking at the Gaussian function, this is related to the standard, the normal distribution, also known as the Gaussian distribution, right? So this is really, if you look at this function, this one here, so I'll just say that yeah, it is related to the Gaussian distribution. But anyway, this is the similarity function here. So so as discussed here, Dr. Ng's video uses this formulation for the Gaussian function, and our textbook uses the slightly different form, but they really are equivalent. So the parameter here of gamma, right? So this is gamma in the formulation from the textbook. And in this one, so this is closer to how you would see it when you discuss a normal distribution. So they usually use a sigma parameter here for the standard deviation. Okay, and again, these are also related in those contexts, right? So in this formulation, it's sigma, but you can just relate those. So like is shown here, and this is some of the stuff you have to do in the current assignment. Also, is basically kind of the same thing as being discussed here. If you're using if you're using a Gaussian radial basis function from scikit-learn, it uses, I believe it uses this formulation, which is why the textbook introduces this. So you have to give a gamma parameter. But if you see this in other contexts, you would specify sigma parameter, but if you need to, you could always convert between one and the other. Right? And again, there's really kind of no good reason for why there's kind of two different variations of this. It's more of historical. So some groups of people used it one way, and some people use it in the other way, even though they're kind of equivalent. So you might run across one or the other. So as hopefully as is shown in here, the scikit-learn, you basically have to specify the gamma here. It's gonna affect these similarity measures the way it's shown by when you're varying gamma here. So to step back on this, so all these do is, let's say we have a single feature. So again, this is coming directly from the textbook here. So let's say we have a single feature. So we might pick two different landmarks. So from one feature, we can calculate two similarity features, right? So whenever x1 is -2, any new data set, the closer it is to -2, the higher similarity is going to be, right? And the shape of these are basically that kind of that bell curve shape, and this comes directly from this expression, right? So basically, the similarity is going to be 1 when you're exactly at the landmark, right? So if our landmark is at -2, we get a 1 similarity for all other new features that we calculate being similar to the x1 equals -2. And the further away you get from that, the less the similarity becomes. So it varies from 1 to 0 in this bell curve kind of shape. And so the gamma or the sigma parameter basically is controlling the width of that, right? So so we show this here. Again, this is also from the textbook. So here we're using where you specify gamma, and we're showing what happens if you plot like a gamma of 5. That's what the green dash one is, and a gamma of 0.1, which is what the blue dash one. So so for the first one, and using gamma, so using gamma like you'd find it in scikit-learn. As is shown here, when you have high values of gamma, you have a very narrow function, right? So it means you have to be pretty close to the landmark to get high similarity, right? And it falls off really quickly. Whereas if you have low gamma, small gamma, it falls off a lot slower. So the similarity curve is much broader. So you'll still have a pretty high similarity even when you're relatively far away from the landmark. And if you're using sigma instead of gamma, it would be reversed, right? So for sigma, since this version divides by that sigma metaparameter, if you have a low value of sigma, it would look more like a high value of gamma. If you have a high value of sigma, it would more like it'd be the same as having a low value for the gamma. So that's all that's happening with the sigma and the gamma. It's kind of a metaparameter. When you use radial basis functions in scikit-learn, it will default probably to something like a sigma of 1. And again, so that's something that you can, sometimes you can get better models if you search and find a little bit better of a value of that for your data set. So sometimes wider similarities or more narrow similarities will get better results depending on the data set. So to give you an intuition of how of kind of what's happening when you use, so when you're going to transform your original features into a set of these similarity features, this isn't exactly the way it's done, but this is, if you think of it as being done this way, as is described here. That's probably good enough for this course to understand what happens when you apply a radial basis function in order to get a nonlinear decision map. If we have just a single feature, again, x1 here, that's not linearly separable, right? So all the values from -2 to 2 are going to be the negative class, and things less than -2 or greater than 2 belong to the positive class. So not linearly separable, but we could apply a Gaussian function to define two new features. Okay. So again, the normal way this is done when you do the kernel trick is really one landmark is going to be for every feature for the training data set just becomes a landmark that we calculate similarities to. Okay. So we don't normally do something like this when we apply the kernel trick, having two similarity features being derived from one of the original features. So that is a difference, but the effects is kind of the same as what's happening here. So in this case, we're going to pick 1 and -2 as our landmarks. So then we'll be able to generate the similarity of each of the original single features to the two landmarks. So for example, this point -2 here has a similarity of 1, so it's going to be 1 on x2, but it has a similarity close to 0, so like 0.05 or something like that for the x3 feature. And if we look at like one of these points here, like -3 is going to be somewhat high on the x2 landmark and close to 0 on the x3. So if we if we calculate the similarity between all of the original features and replot them, we get this. So now these are what it looks like on x2 and x3. And again, these points were picked, and we had to use two features so that we would get something that was linearly separable in this case. So in this case, so it's easy. So now we can apply, logistic regression or the support vector machine cost function to our transform, kernel similarity features, and it will be able to cleanly separate those. So we'll get something that will actually perform well, at least on the data that we train it with. That originally wasn't linearly separable. Okay, so anyway, just to finish up on that, so if you look through kind of the last part of the assignment on the support vector machines, or even the first part, well, the second part we're working with a nonlinear classifier. Basically, it can be done like this, right? So if you use the SVC from, which is the support vector classifier from scikit-learn, you can use different kernels like radial basis function kernels. Let me see if I can bring up the help here, contextual help. I rerun my rerun all my cells. Let me see if I can rerun all my cells here. Because I wanted to bring up the contextual help here. So and notice that if you specify the RBF, which is a radial basis function kernel, which is basically this Gaussian similarity kernel that we were looking at, you can specify then the gamma parameter, and the gamma will default to this using the scale here. So looking these up, you can use linear, polynomial, radial basis function, and then there's two others, different kinds of kernel, sigmoid, pre-computed, that you can pass in. So I believe you can actually create your own kernels and use them this like this. So and then things like, for example, gamma is a coefficient that only makes sense for radial basis polynomial and sigmoid kernels here. So, and it describes here. So, if you don't specify gamma, it's basically doing something based on the variance in the training dataset features in order to pick what would usually be a reasonable value for gamma there. Okay? So that's what the scale is doing by default. But anyway, yeah, as shown here, if you have a nonlinear data set, like again, we're back to using the moon's data set here. Another thing I should mention, I don't remember if we emphasized this in our assignment, but support vector machines can be sensitive to the scale of the features. So if we didn't specify it, we probably should have in the assignment. So usually for support vector machines and a lot of parameterized models, you really need to make certain that all the features are on a similar scale, or you can get results that don't work very well, right? So support vector machines are one of those classes of models that can be sensitive to that kind of thing. So it's usually a good idea to always put them through some sort of a scale all the features, like using a standard scaler or some other kind of scaling method, right? Which is what we're doing on these examples here. But otherwise, and you can still use the C parameter. So notice if we have C too small, so even though if we're using a nonlinear kernel, if we give it lots of regularization, we're going to force it back to more like a linear model. Right? So C was kind of too small here, so it tries to make the model as simple as possible, kind of more like a line. Where if you use a C that's reasonable, or this was maybe a little bit too big here, but yeah, you'll get something that fits better. But yeah, this discussion here was also trying to show the effect both of C and varying gamma at the same time. Right? So here we had a small C and a small gamma, a small C and a large gamma, which looked like give a relatively reasonable fit. And then we have a large gamma and a small C, right? And then both gamma and C being marked. Right? So here, at this end, we might be overfitting too much. Example that we have. Okay, so I'm just going to wrap up talking about the support vector machines. Those are the basic things to understand about how these kernel methods apply to support vector machines. And kind of in summary, the most common one to use is this radial basis function, which is really a kind of a Gaussian similarity. And you're asked basically in the assignment that you can still be working on right now. You should be working on it right now. To implement the Gaussian similarity by hand and use that to fit a nonlinear decision boundary for the data set used for the current assignment. Just a final thing, this is brought up in the textbook. You can also use the support vector machine cost function to do a regression instead of a classification. The trick on that is you reverse the idea of instead of kind of minimizing the boundary violations, you want to maximize them. Right? So you'll fit a function when you're doing a using support vector machine for regression. You're going to fit a function that tries to get as much things as possible within a small of a margin as possible. So that's kind of what to think about what it's doing. And I think this discussion shows kind of doing it by hand, but there is a version in scikit-learn the SVR. So if you just use SVR, support vector regression, it will be fitting a line to the data. So it does the modifications, so it's using the correct version of kind of the idea of the cost function to try and maximize the boundary violations. So usually, if you compare support vector machine regression with just a standard linear regression, you should usually maybe not get exactly the same result, but get a pretty close result. Right? So for a set of data. And likewise, you can use a kernel function to get a nonlinear function regression line to a set of data. So shown that as well, again from the textbook here, where we have data that's the made up data here is really just a degree 2 polynomial. And we're using the SVR again, support vector regression, with a polynomial kernel again. So we end up with a nonlinear regression line in this case. Okay, so I think that's. I think I'll leave that there. So let me know if anybody has any questions on that or thing. So I had some questions here. Yeah. So I had misspoken when I was talking a little bit. So we've got assignment 5 due this Friday, and assignment 6 then will be due in 2 weeks. So starting next week, we're going to be starting looking at what are known as ensembles and tree methods, and assignment 6 is on that. So you'll have 2 weeks after this Friday for the assignment 6. And yeah, I'll check the due date. So I still maybe don't have all the dates set correctly for everything coming up here. So yeah, it should be due on the 24th, the assignment 6. All right. So yeah, I won't spend too long with this. Like I said, I kind of threw in k-nearest neighbors and naive Bayes because our textbook doesn't really have these, but I think it is a good idea to become familiar with other machine learning methods. So there's one particular thing for k-nearest neighbors that I think is useful to know about here. So anyway, so k-nearest neighbors is a little bit different. So we really haven't looked at non-parametric models yet in this class. This is kind of really the first one, I think, that we kind of talked about in a little bit of detail. But so some machine learning classes actually start with KNN rather than start with like linear regression, which makes sense because it's really very simple. It's simpler, much simpler than applying a linear regression as a model here. So KNN, K nearest neighbors, probably makes most sense. You can think of it as in terms of doing a classification again. Okay, so let's say we need to classify some data, and let's say we have these two different data sets, the kind of purplish and the red ones here. Right? So if this is all the data we have, this is a relatively clean data set, it's linearly separable. So most classifiers would work well with this, assuming that this data is relatively representative and it is our two different classes are relatively well separated. So for K nearest neighbor, the idea is if I have a new data point, we're going to find the nearest neighbors. So in K nearest neighbors, K is a metaparameter, which is you specify that as the number of the nearest neighbors to a point that we're going to consider when we're making our decision, our classification decision. Okay. So one thing about K nearest neighbors is there's no fitting. Right? So it's not a parametric model. So when we have a data set, we don't have to do anything beforehand in order to make a classification. All the work comes when we're going to make the classification decision. Right? So if we want to determine what class the point X is here using K nearest neighbors, this is kind of in between, so it's going to be kind of ambiguous whether we would have it as kind of the red or the purple here. So for K nearest neighbors, we have to have some measure of, again, of similarity or nearness, right? So usually the Euclidean distance is used, right? So if each of these features, if you just think of these as a point in n-dimensional space, we can calculate the distance between the point we want to classify and all of the other data points. And then we can sort them and find the three closest, so the three with the smallest distance to the point we want to classify, if we're using a K of 3, or the three nearest neighbors in this case. And at that point, then it just becomes a voting kind of thing. So, I mean, you can use some sort of scaling, so you can take into consideration the distance as well as the class, right? So I'm bringing up that there's some more complications that I'm going to actually discuss here in this notebook. So you have to make some variations, like if we're using a multi-class classifier here, it's possible that our neighbors, instead of having 2 classes, there might be 3, 4, 5 classes. So then they have to worry about if I'm using just straight up majority vote. How's that going to work? What would happen if I have a tie? Right? So if I use the 4 nearest neighbors and I have 2 of the red and 2 of the blue, we just use a straight up vote. How do we break ties and stuff like that? So, but yeah, the simplest idea is just use like an odd number of neighbors. If we have just a binary classification task, the majority is going to be the winner. So in this case, the 3 nearest neighbors, 2 of them are red, and 1 is the purple, so we would predict that this is the red class here. If we move this one a little bit like over here, so that this point was closer than that point, we would end up having these 2 and that one as the nearest neighbor. So we'll end up picking blue in that case. And as you can maybe kind of see, K nearest neighbors isn't necessarily going to give you a linear decision boundary, right? So depending on any point here, it's going to depend on what are the 3 closest points. So that will vary that can vary in a nonlinear way if you systematically figure out every point on this two different features, X and Y here, what they would end up being classified in using like the three nearest neighbors. So anyway, it's pretty easy to actually implement k nearest neighbors by hand. K nearest neighbors doesn't have any fitting, like I already mentioned. So all you have to do is, you have to have your data set. You have to have some way then, so for the predict method for k nearest neighbors, I just need to calculate the distance. And the most basic way of calculating distance is just use the standard Euclidean distance. So the sum of the square root of the sum of the squares to give you the Euclidean distance between the point you're trying to predict and all the other points, and then you'd have to sort those to get the k nearest ones, and then come up with some sort of a voting. So either just a hard vote, majority vote, or a common variation is to scale the class by the distance. So you give more weight to things that are really close and less weight to the points that are far away for your nearest neighbors. You're using a scaling when you're doing your voting there. So yeah, to summarize all that, it's very easy to implement, very easy to understand, which is why it's often seen as kind of a first algorithm that's discussed in some machine learning classes and textbooks. There's no cost for it's not a parameterized model, so you don't have to fit the model in order to figure out what the parameters are, like you do for linear regression and logistic regression or support vector machines. But all the algorithmic cost comes at the prediction side, and it can be not great on performance because you do have to calculate the distance for every prediction between that point and every other point in the data set. Right? So it scales with the size of the data set that you're using for your K&N model here. There's other technical things. So mathematically, it doesn't work very well for large data. So once you have high dimensional spaces, so once you have a large number of features, the distance between things becomes a bit non-intuitive. So it tends to only work well when you have tens to hundreds of features at most. So. Okay, yeah, so I think, so maybe the last thing I'll mention, so the K is kind of the only metaparameter that's used with K nearest neighbors. So well, it's not the only one, so, whether you're using scaling or not, there are other functions rather than just straight Euclidean distance that you could potentially use. So again, let's see if I can run this notebook. We can look at the contextual help here. Get an idea of the different things that you can do with scikit-learn here for the k-neighbors classifier. But yeah, usually the number of neighbors is the most obvious kind of metaparameter that's going to affect the performance. So for a given data set, smaller or bigger number of neighbors will give you better performance usually. But yeah, some of the other parameters you can pass, you can use in scikit-learn for the k-neighbors classifier are This is what I was talking about. So if you use a uniform weighting, it's just going to be like a majority vote, where if you scale by the distance or the similarity, it will give more weight to closer ones when it's figuring out which class is going to predict, and less weight to far away points for the neighbors. So yeah, the P here is actually use something other than 2, you'll be getting something that's actually not Euclidean distance. So again, this is, if you know mathematics, a little bit about different ways of calculating the distance. A P of 1 gives you what's known as the Manhattan distance. So that one you only just use like walking city blocks instead of straight lines. But you can now actually use bigger ones than these, than 2 as well. But usually Euclidean distance. Usually you won't get much difference from these. So the default is just to use the L2 Euclidean distance here. So a common thing to do would be, though, to maybe at least explore what size of K you want to use. So the number of neighbors, which is kind of, I think, the last thing the textbook is showing here. So using a K of 5 gives about the best results, and when you get larger values of K or smaller, get a little bit bigger errors here. So here, smaller is better on this error rate. All right, so let's see. Yeah, one final question, I guess. In assignment, in the task 3.3, yeah, so I think it's like you said. So it asks which cells are supposed to be added to. Let's see if I can bring that up real quickly here. So that's not right. So so yeah, at the very end, trying to lead you through, step you through, kind of comparing your own hand-built version of the Gaussian radial basis function and the built-in one. So yeah, I mean, really the code that's given to you should do that. You only need to visualize again the decision boundary that ends up being resulting from using the built-in kernel. So the last part here we're showing. No, so we're showing using the hand-created kernel. Yeah. So this is supposed to be just. It does show you how to pass in your own hand-built function. This ultimately should be calling the function that you wrote to implement the Gaussian kernel, so the Gaussian similarity. Right? But yeah, given that, you should be able to then just show the resulting decision boundary. You should get the same decision boundary basically as what the scikit-learn gets by using the RBF. All right. I think that's it for today. I'm going to go ahead and wrap up. We'll meet again Thursday. I might talk a little bit about the naive Bayes. I'm not certain if I have too much to say on that, but also we'll see if there's anybody has some more questions about support vector machines or k-nearest neighbors or things like that. So, all right, that's it for today. Hopefully everybody has a good week. Keep working on the assignments, and I'll talk to you guys all later.